Alright, so let's look at this problem here. So we have a string being used to pull, to pull two blocks. Block 1, which is connected to block 2 by another string. So block 1 has a mass of 2 kilograms and block 2 has a mass of 5 kilograms. There's negligible friction between the blocks and the surface. The tension in the rope pulling block 1 is 21 newtons, and let's calculate the tension in the rope connecting the two blocks. Alright, so let's first kind of just sketch out the situation here. We don't know which way the two blocks are moving, so it doesn't really matter which way we draw it, but I'm going to assume that we've got, let's say, block 2 here on the left, and it's connected by a string to block 1, which there's another string connected to it, where we know the tension in that string, which we'll call T1, let's say, is 21 newtons. And we know there's some other tension in the string in between the two, and we also know the masses, so maybe I'll list that here. Block 1, so mass 1 is 2 kilogram. And mass 2 is 5 kilogram. Okay, so in this problem, we do, at least partially, have to consider both objects separately, if only because we need to account for the tension in between them. Although we can take the approach of solving this because we don't know the acceleration, right? So we could determine the acceleration of both these objects together by considering them as one combined mass of a 7 kilogram object moving together, find the acceleration, use that to find some other missing information. But I'm going to draw two free body diagrams, one for object 2 and one for object 1. So let's first, I'm going to draw my free body diagram a little bit inappropriately here, in the sense that I'm just going to draw a box with 2 on it, just to remind myself that's block 2. Typically in a free body diagram, we depict our object as a point mass. But anyway, we've got a couple forces acting here. We've got the tension on block 2, and that's in the direction of the string, which is straight to the right. We'll call that tension 2. And then other forces acting on this block, well, there's no friction, but always, since the object has mass, we have the force of gravity. That's going to be acting straight down. So this is the force of gravity on object 2. Counteracting that, we have a normal force straight up. This is normal force acting on object 2. I know those are equal and opposite in magnitude only because our object is accelerating only horizontally. So therefore vertically there has to be no net force. No friction or anything. Okay, so that's all the forces we have acting on block 2. So block 1, all right, well, let's see. Again, we have friction and normal force. So we've got force of gravity acting on object 1 straight down, and normal force acting on object 1 straight up. I drew those smaller because that block has less mass. Other forces. Well, let's see. There's two strings acting on block 1. We've got the string, one string acting to the left, that's connecting to the other block. All right, and that's tension 2, right? It's the same string, so it's the same tension. And that I drew equal and opposite to the tension 2 acting on block 2. This is actually a Newton third law pair. Then we've got the other string, the 21 Newton force. So that's T1. All right, and I drew that longer just because I'm expecting that in this problem, that like if these blocks were at rest, the fact that we're pulling on the rope and on block 1, tension 1, is going to cause the whole system to accelerate. I could be wrong about that, but I'll make that assumption. So then here, okay, so since we want to find the tension 2, that's acting horizontally. So when we're applying Newton's second law, it's going to make sense to do so horizontally on at least, let's see, object 2 here. All right, so if we sum the forces in the horizontal direction for object 2, right, well, first we need to be clear and pick a positive direction. So since I'm assuming the acceleration's rightward, I'm going to call rightward my positive x direction. So if rightward is positive x, my net force is going to be mass times acceleration. I need to be careful here and add my subscript of 2 for the mass since we're summing the forces on object 2. Alright, so now let me actually sum our forces here. And rightward is positive. Well, we only have one horizontal force and no other forces are acting horizontally or even have any components. So it's just going to be tension 2. So it'd be really nice if, all I had to do was just use this formula, right? I'm solving for tension 2. That's my end goal in this problem. We know mass 2, but we don't know acceleration. So right now I have one equation and 2 unknowns, so I can't solve this yet. I need one more equation. So I'm going to do that by summing the forces on object 1. So the reason why I'm doing that is because we want to get rid of acceleration, right? We want to solve for tension. So since acceleration is going on horizontally, I still need to sum the forces horizontally. So summing the forces in the horizontal direction on object 1, that's now going to be the mass of object 1 times acceleration. And writing an expression for adding up of the horizontal forces, we've got a positive tension 1 and a negative tension 2. So in terms of solving a system of equations, right, I need to solve this system of equations where my unknowns are acceleration and tension. Tension 2, excuse me. So since I'm trying to solve for tension 2, I need to rearrange one of these equations for acceleration and plug that into the other. Looking at this, it's going to be simpler to rearrange this first equation. All right, so this first equation gives us that acceleration is simply tension 2 divided by mass 2. So I can take that acceleration and then plug it into my other equation. So we end up with, actually I'm going to continue writing up top here. We've got mass 1 times acceleration, which we found to be t2 divided by m2, is equal to t1 minus t2. So now our expression, we have one equation with one unknown. The only thing we don't know is tension 2. So that's great. Thing is now we need to simplify because we want t2 to be all in one term. Right now there's 2 terms with t2. First thing I'm going to do is make my left-hand side look a little prettier here by factoring out m2. So I have m1 divided by m2 multiplied by t2 is equal to t1 minus t2. I'm going to add t2 to both sides, so that way at least all my t's are on the same side together. So we have m1 over m2 times t2 plus t2 is equal to t1. So now on my left-hand side here, I can factor out t2 from each term. So I have t2 times the quantity of m1 divided by m2 plus 1 is equal to t1. And I can double check that I did that right by multiplying back in to see that I get the same expression I just had. So the last thing, all I need to do is divide by these parentheses on both sides. So I have t1 divided by the whole quantity of m1 over m2 plus 1. So when plugging in numbers here, t1, that's 21 newtons, divided by m1, which is 2 kilograms, divided by m2, which is 5 kilograms, plus the quantity 1. And in the end, this gives us 15 newtons. So the magnitude of this tension force is 15 newtons. All right.